Right now, in your house, there is an echo of the Big Bang. Turn on an old analog television and tune it between channels. Roughly 1% of the static you see is actual cosmic microwave background radiation. Light that has been traveling toward you for 13.8 billion years. The Big Bang is not a theory in the casual sense. It is one of the most thoroughly tested ideas in all of science. We have direct evidence. We have measurements accurate to 4 decimal places. And the picture they reveal is genuinely difficult to believe. 13.8 billion years ago, the entire universe, all of space, all of time, all of matter and energy, was compressed into a region smaller than a single atom. Not just the matter we can see today. Everything, every galaxy, every star, every atom in your body, all of it, concentrated in a point. And then it expanded, not into anything. There was no outside. Space itself expanded. The universe did not explode into existing space. The expansion of space was the universe. This is one of the hardest ideas in modern physics to grasp, because every analogy fails. The Big Bang was not an event in space. It was the event that made space. How do we know this happened? The story of the discovery begins in 1929. An American astronomer named Edwin Hubble made a measurement that changed cosmology forever. He noticed that the light from distant galaxies was shifted toward red. The further away the galaxy, the more its light was stretched. This is called redshift, and there is only one good explanation. The galaxies are moving away from us. And the further away they are, the faster they are moving. But here is the key point. They are not moving away from us specifically. They are moving away from everything. Every galaxy is moving away from every other galaxy. The space between them is expanding. If the universe is expanding, then in the past it must have been smaller. And in the more distant past, smaller still. Run the clock backward far enough, and everything we see today converges to a single point. A moment of infinite density. The Big Bang. Now here is what we do not know. We do not know what was at that point. The mathematics of general relativity breaks down at the singularity. The laws of physics we use to describe the universe fail to describe the very beginning of it. What we can describe with confidence is what happened starting 1/10 millionth of a trillionth of a trillionth of a trillionth of a second after the beginning. In that unimaginably small fraction of a second, the universe underwent a period of exponential expansion called inflation. In less than a billionth of a billionth of a billionth of a second, the universe expanded by a factor of 100 trillion trillion. It went from smaller than an atom to roughly the size of a grapefruit. After inflation ended, the universe was a dense, hot soup of fundamental particles. Quarks, electrons, photons, all moving at nearly the speed of light. The temperature was around a billion degrees. It was not yet a universe of atoms. It was too hot. Any atom that tried to form would be immediately torn apart by the heat. Then, in the first 3 minutes, something extraordinary happened. As the universe expanded, it cooled. Within seconds, quarks combined to form protons and neutrons. Within minutes, those protons and neutrons fused together to make the first atomic nuclei. The first 3 minutes of the universe built the simplest elements on the periodic table. Hydrogen, helium, a tiny amount of lithium. This is called Big Bang nucleosynthesis. And we can verify it. The prediction is precise. The universe should be roughly 75% hydrogen, 25% helium, and a trace of lithium. Everything else, every element heavier than lithium, was forged later, inside stars and supernovae. We covered this in the periodic table episode. When astronomers measure the actual abundance of elements in the universe, the numbers match the Big Bang prediction within fractions of a percent. But there is even stronger evidence than this. And it came from an accident. In 1964, 2 American radio engineers named Arno Penzias and Robert Wilson were testing a very sensitive antenna at Bell Laboratories in New Jersey. They kept picking up a faint hiss of microwave noise from every direction in the sky. They tried everything to remove it. They cleaned the antenna. They removed the pigeons nesting inside it. They scrubbed the pigeon droppings. The hiss remained. Eventually they learned that physicists at nearby Princeton had predicted exactly this noise. It was the cosmic microwave background, the cooled down afterglow of the Big Bang itself. Penzias and Wilson had stumbled onto direct evidence of the universe's beginning. They received the Nobel Prize in 1978. The cosmic microwave background is the most important map in cosmology. It is light from when the universe was only 380,000 years old. Before then, the universe was a hot fog of charged particles. Light could not travel through it. At 380,000 years, the universe cooled enough for electrons to combine with protons to form neutral hydrogen atoms. Light could finally escape. That light has been traveling toward us ever since. Stretched and cooled by the expansion of the universe, it now arrives as microwave radiation at a temperature of 2.725 degrees above absolute zero. We have mapped it with extraordinary precision using satellites like COBE, WMAP, and Planck. The tiny variations in the map, temperature differences of 1 part in 100,000, are the seeds from which every galaxy formed. After the cosmic microwave background was released, the universe entered what astronomers call the Dark Ages. No stars yet, no galaxies, just clouds of hydrogen and helium gas, slowly clumping together under gravity. This lasted around 200 million years. Then the first stars ignited. Their gravity pulled gas into denser and denser clouds, until the temperature and pressure became high enough to begin nuclear fusion. These first stars were giants, hundreds of times the mass of our Sun. They lived briefly, they died in spectacular supernovae, and they began the process of building every element heavier than helium. Generations of stars came and went. Each generation built more heavy elements. Each generation seeded the next. By around 13 billion years ago, the first galaxies were forming. Around 9 billion years ago, the Sun and Solar System would later condense from one of those clouds. 4.54 billion years ago, the Earth formed. We covered that story in the last episode. What does this all add up to? The universe is 13.8 billion years old. We know its age with an uncertainty of about 0.2%. That is a more precise number than we have for many things in physics that we encounter every day. We can see the cosmic microwave background. We can measure the expansion rate. We can verify the predicted abundance of elements. The picture is consistent. But there is one question that the Big Bang does not answer. What came before? The honest answer is that we do not know. The mathematics breaks down at the moment of the singularity. The laws of physics may not apply. Time itself may not have existed. Some physicists argue the question is meaningless. Others argue that we simply do not yet have the right physics. Some theories suggest the universe could be one of many. A multiverse, each one with its own laws of physics, its own constants, its own beginning. Our universe just happens to be one where stars and atoms and life are possible. Other theories suggest the universe is cyclical, that it expands, eventually collapses, and begins again. We have no way yet to test these ideas. What we do know is the trajectory we are on. The universe is not just expanding. The expansion is accelerating. A mysterious force called dark energy is pushing galaxies apart faster and faster. Trillions of years from now, the universe will be dark, cold, empty, galaxies separated by distances so vast that no light can cross. But that is the deep future. For now, the universe is in the middle of its life. Stars are still being born. Galaxies still glow. Light still travels across vast distances and arrives in your eyes from places too far away to comprehend. And the echo of the moment it all began is still arriving on Earth, right now. From the largest scales of cosmology, the next episode takes us in the opposite direction. To the smallest scale of intervention humanity has ever attempted. The moment a species learned to edit its own DNA. CRISPR, the tool that could rewrite life itself. That is the subject of the next episode. The Big Bang, 13.8 billion years ago. The beginning of everything. If this changed how you see the universe, subscribe to Knowable. Drop a comment. What is the most surprising thing you learned today? New science explained as every week. See you next time.